In this video, we will study the linear least square estimation problem. So the linear least square estimation technique is one of the most important and useful techniques in static estimation. Before we formally introduce it, let's first discuss what is static estimation. The definition of static estimation is very simple. It just means the state of the system is static. In other words, x dot is equal to 0. The measurement of the system can be very general nonlinear. That means that y equal to h of x plus v, in which v is the measurement noise. The goal of static estimation is basically just estimate x given 1 or more y. That means mathematically we want to find a function g of y which gives the estimate of x, or we find x hat equal to g of y tilde, in which y tilde is a group of all the measurements from y1 to yn. The goal is usually achieved by solving a goal equation or an objective equation. For linear least square estimation, so basically the goal equation is just j equal to y minus hx squared. And we are trying to find the value of x hat which minimizes the value of j, or the value of y minus hx squared. This is the most basic expression. There is a fancier version called weighted least square estimation. So basically the idea is to weight each component in the j function using a weight matrix. And the expression can be written as y minus hx squared weighted on A inverse. To expand it, we can write it as y minus hx transpose multiplied by A inverse multiply y minus hx. So here we want to make it very clear that the result of this expression is just a scalar. So basically we can consider that y is an m-dimensional vector, and therefore y minus hx is just m by 1, and A inverse is m by m, and therefore the transpose is just 1 by m. So therefore the result is just a scalar. Furthermore, we can incorporate the a priori states based on the previous information or knowledge on the value of x. Basically here we assume that x is following a normal distribution with mean as x naught, and therefore the expression for the j function becomes to be in this form. So first of all we repeat the previous expression, and also here we add the expression for the a priori states in this format. Here B is the weight matrix for the a priori state, and this will be a complete form of the least square estimation goal function. For the next, we want to obtain the optimal solution for the topic of this video, that is the optimal solution for the linear weighted least square estimator. First of all, let's recall what is our system. In our system, the measurement is a linear function, hx plus v, and v is following a normal distribution at 0 and r. The state of the system is static, but is following a priori normal distribution as x naught, bar, and p naught. For the next, we want to find the best choice for j. First of all, let's recall the expression for the goal function. Here we are using r and p naught as the weight matrix. This makes sense since r and p naught are the covariance of the states. Therefore, their inverse represents the confidence we have in the states. For this reason, we can use them as the weight or confidence we can have on the components of the J function. For the next, we want to obtain the optimal estimate for the state. We can achieve this by doing partial derivative of J with respect to x and set the result equal to 0. The expression for partial J partial x is just the following. You need a little bit of trick of doing partial derivatives, and we can set the result equal to 0. If we solve for x hat, the expression is the following. If we use matrix inversion lemma, we can obtain an alternate format of this expression as the following. So if you are familiar with Kalman filter, you will find that this expression is the exact expression for the update function for a linear Kalman filter. And this term on the line is just the Kalman gain matrix. So therefore, we can write it as x naught plus k multiplied by y minus h x naught. The next question we want to answer is how accurate our estimate is. So we can look at this by evaluating the variance of the estimation error. First of all, recall that the estimation error is defined as the following. If we define it as x tilde is equal to x minus x hat, the true state minus the estimate, and therefore the error covariance is represented as the expectation of the outer product. For the next, let's derive the expression for x tilde. X tilde is just x minus x hat, and if we substitute in the expression for x hat, we get this expression. So here we want to define x naught tilde, which is equal to x minus x naught bar. So therefore, the expression just becomes x naught tilde minus k multiplied by this term in this brackets. So if we combine some terms, the final expression is just I minus kh multiplied by x naught tilde minus kv. For the next, let's evaluate the outer product. If we substitute in x tilde, we will get 4 terms. The first 2 terms are symmetric, and the last 2 terms are asymmetric, as the following. With this outer product, we can evaluate the expectation of them, which is the value of the P matrix. And the result is based on a few assumptions. So first of all, we assume that the expectation for x tilde multiplied by V transpose is equal to 0. And also, we assume that the expectation from x naught tilde multiplied by V transpose is equal to 0. So this just means that the states and the measurement noise is not correlated. And also, we realize that the expectation for x naught tilde transpose is just p naught. and the expectation of VV transpose is just R. So with those results, we are ready to derive the expression for P. So it would be very simple. The first term will sustain and give the following results, and the last two terms, the asymmetric terms, they will vanish. And this expression here is the famous Joseph form. And it turns out that we can also obtain some alternate form using the matrix inversion lemma, and they are also very commonly used. So this is the second one, and also we will have a third one. In the following, we want to address the problem of multiple measurements. So in the system, we assume that yi is equal to hi multiplied by x plus vi, in which vi is the following normal distribution of 0 and ri, and we can have a number of n measurements. So how to solve this? So the solution is that we can build a solution by construction. So for example, we can construct a big y vector as y through yn, similarly h as h1 through hn, and v as v1 through vn. And of course, in this case, we can write the system into y equal to hx plus v, and v is following a normal distribution at 0r, and r is just a diagonal matrix with all the R matrix R1 through Rn. And in this case, we can just directly write the expression for the optimal estimate just in the same format as the previous one, because we did a good job on the construction of the problem, basically. And we can also obtain the P matrix similarly. But there is a drawback of this system, that is, now we are dealing higher dimension than the original system. So it turns out that we can have an alternate solution to go around this higher dimension. So we can, in this alternate solution, we can obtain xi just for the based on the measurement of yi and x naught. Similarly, we can obtain just pi based on p naught and ri. And the trick here is to how to combine those xi and pi. So first of all, we combine pi in this form into the final covariance matrix P. So this is a quite famous formula, and with P we can obtain the final estimate in this format. So therefore, as you can see here, now this solution is low dimension, is equal to the dimension of the original system, and it's also flexible in adding new measurements. But of course, the payoff is that the expression is not that simple. Alright, that's pretty much the end of this video. In the next video, I will introduce the MATLAB program for linear least square estimation. So please do check that out. Also, if you enjoyed this video, please hit the like button. Thank you. Have a nice day.